Engineering Human Perception from University of South Florida, University of Oklahoma, and American University at Washington, D.C. So Ray, go ahead.
Hi, everyone. My name is Ridwan from University of South Florida. So today I'm going to present my paper, Perception-Aware Attack Creating Adversarial Music, where reverse engineering human perception. So this is a joint work with Zhe Qu, Shangqing Zhao, Lei Ding, Yao Liu, and Zhuo Lu. Audio classification systems, such as speech and speaker recognition, are more and more popular in recent years. However, these systems are vulnerable to adversarial samples. For example, attackers can add a small perturbation to the original signal, and it can mislead the system to predict the wrong label. Recently, this threat has been extended to the music copyright domain. When user upload a copyright music to his own YouTube channel, the YouTube will report a copyright claim to this video, and this video is prohibited to be monetized. However, attackers can easily add some perturbation to revise the audio fingerprints, and then it can spoof the YouTube detection, and this time attackers can monetize from this video and without paying any copyright fees to the original owners. But if we listen to this music, we will feel a little bit noisy and distorted, which could limit the real-world impact. So if we look at the problem formulation of existing work, we could find that they commonly use a mathematical distance to minimize the perturbation, for example, the LP norm. However, there's no evidence to show that LP norm is a good matrix to evaluate human perception of music. So there exists a large gap between the mathematical distance and the eventual human perception. So in this paper, we propose to explore the key insight of music perception and aim to create a better perception of music. So first, we should know there are mainly 4 features for music perception. They are pitch, rhythm, timbre, and loudness. For pitch, it can be described as the highness or lowness of a sound. Rhythm indicates the tempo of music is fast or slow. And for timbre, it can be considered as a color of harmonics. For example, piano and trumpet, they have different sound quality of a music note. And last, for the loudness, it is similar to the LP norm, which describes the volume of a sound. Since we know there are 4 features in musical perception, and how does the existing adversarial samples affect these features? Here is an example from existing work, ICML20. So first, if we look at the loudness, we can find that there's only a small change in the time domain. But if we focus on the frequency domain, we could find that the third harmonic is suppressed, which will bring in harmonic to the original signal, and it is harmful to the timbre feature. And then if we take a look at the pitch, we can find the largest distance is nearly 2,000 cents, which can be easily recognized by human ears. And the last one is rhythm. We see the DTW path between the original and the perturbed signal is tortuous, which could make the music sound weird. So we know these features can be more or less affected by the perturbation. So we propose to explore one step further to find a jointly solution from both human perception and attack effectiveness. So first, for the human perception, we want to find the perception-friendly features. For example, which features dominate the human perception? And on the other hand, we could find which features are effective in the audio fingerprinting. And then we jointly these features as our solution. To build our human perception model, we use human ratings as labels and the feature deviation as inputs to train different regression models. and we find the best model named as QDV. And based on this model, we do sensitive analysis. And we found that all the features are important to the human perception. So we propose to only change one feature. On the other side, when we look at the audio fingerprinting, we can see that all the fingerprints, they are located as a harmonics. So we can revise harmonics, which indicates timbre is a feasible feature. So combining with the previous finding, we propose to only manipulate timbre and then remain the pitch and the rhythm as much as possible. So to only revise timbre and keep the same pitch and rhythm, we can play the same piano roll with different instrument tracks. So in this way, our perception-aware attack can be formulated as a constraint optimization that finding a linear weight of additive instruments. When the QDV is minimized, we can find the best perceptual music, and then it can bypass YouTube at the same time. Here is the experiment result. We invite 2 group volunteers. From this figure, we can see that our perception-aware attack can always achieve good perception from both groups. However, for SCM20, we see that they are a little bit noisy. And for psychoacoustic attack, they can achieve better, but still a large difference to our attack. And we also evaluate the attack effectiveness. We can see that under the same attack success rate, our method can always achieve much better performance. So here we provide 3 adversarial samples from different methods. The first one is from SCM20, which is failed to bypass YouTube.
What would I do without your smart mouth? Drawing me in and you kicking me out.
Okay, so next is for psychoacoustic.
What would I do without your smart mouth? Drawing me in and you kicking me out.
Okay, the last one is for our perception-aware attack.
What would I do without your smart mouth? Drawing me in and you kicking me out.
Okay, so in conclusion, we conduct a human study to build a human perception model, and we reverse engineering this model to formulate our perception-aware attack. And based on our attack, we can create a better perceptual music and also bypass YouTube. So if you are interested in our work, you can find more samples in our paper. Thank you.